So what I have here is a piece of fence, and let's look at what it looks like. I have it. This is an expanded metal fence, so you can see the what it looks like. Or we can have our barbed wire and chain link if we wanted, or if we wanted this on an angle, we can do that as well. It's all whatever you set up your model to be, so it's not a big deal either way. But let's look at what we want to do. I want to bring in a piece of fence and bring it in here. And let's see, I need a piece of fence here, need a piece of fence here. So let's look at adding a piece of fence here. So I'm going to come in here, I'm going to place a piece of fence. Let's see, expanded metal, your chain link. Let's open this guy. And put a piece of chain link in here. Here's my chain link. I'm going to make it adaptive. I'm going to take my chain link and I'm going to take the axis, the z-axis. I'm going to make that. Hold on. Make sure I do this right. Okay. So I want to mate it over to this end. All right. So what I have here, to be clear, I have a fence skeleton, because this is substation modeling strategy, talks about skeletons. In the skeleton for the fence, I've placed work axes at key points, and that's where I'm going to have a corner post. So my corner posts are going to be on those work axes. So what I'm going to do, I'm going to place this piece of fence I just placed in. I'm going to constrain that to, let's look at my fence skeleton and my work axes. Let's find that guy. There it is there. Let's constrain that together. Now I'm going to constrain it. I know my XY planes are my reference planes, so I can just quickly go flush, come up to flush up here. So now I got my piece of fence. It's not aligned yet, so let's align it to my skeleton. So let's come back down here. I know how I've drawn this, so I can take that axis and constrain it to my skeleton. Now everything's constrained. I can't move that at all, right? But let's look at what I'm talking about adaptive. We have our little circle, blue-red circle, meaning it's adaptive. What is adaptive is the work plane. This is a key point here, is that my work plane, my work geometry is adaptive. Not my features, not my sketch, my work plane is. That is key. So let's come in here. I'll break that down in a minute, but let's constrain this work plane. I want to constrain it to my axis there and apply. And there is my fence stretched out accordingly. All right. Now my posts are I put in separately. In this case, I can make them adaptive, but it makes it very complex to make the posts adaptive, but it can do. I'm not using any eye logic here. This is just normal Inventor practice to be able to do that. So let's take a look at my chain link adaptive template. So here it is here. So I have all my work geometry at the top of my browser. They're all made from the origin. So it's a very robust piece. I have my end work plane NB and work plane NA. So NA is based on the origin, right? I have my origin planes. If I look at the origin planes, I have it offset by the diameter of the largest post and the railing post, right? So I have the railing. I have 3 railings on here. So that's the way it's set up. It doesn't have to look exactly like this, whatever you guys set up, but the theory behind it is what I want to talk about. If you look at the rails, let's look at the extrusion. Edit feature, it's extruded to. It's extruded to this NB, and the NB is what's adaptive. So if work plane NB moves, whatever length it's going to be in the spacing, the feature, the extrusion of the rails is going to hit NB no matter where it goes. So it's the extrusion is dependent on the work plane, the work geometry. The work geometry is what is mated in the next higher assembly. This makes for a very robust extrusion, adaptive extrusion that's not going to break on you, and it's not going to be upsetting. So there's a couple things I did there. When I extruded it, or when I constrained it, I constrained all my constraints first, and my last constraint was my adaptive constraint. So I mated it to the post location on the skeleton. I don't have it dependent on the post itself. It's dependent on the skeleton. That way I can change the post, move the post, do all kinds of stuff. I have constrained it again to the skeleton for the height. And I've constrained it on the angle to the skeleton again. And these are the three main constraints, but now I add a fourth one for the length, and that gives me the length. If you look at the extrusion for the chain link side, it's the same thing. It's extruded to the work plane, and it's the work plane that is adapted. Now, what a lot of people don't want, and myself included, I don't want adaptive assemblies in my main model. It can cause problems. It can slow things down. If something were to change and one was dependent on another one, next thing you know, you're waiting 10 minutes for your drawing to update. So what I usually do with my fencing is that I will shrink wrap that fencing and put it through. So let's look at what we have for a bill of materials, because we're going to do this right, that we want the bill of material to tell us what the heck's going on. So here's my model data. I have all my information here, all the files, and you look at almost everything's a phantom part, except for my fence pieces. And I'm given a length for each fence piece. Because it's extruded, I've set up my fence piece so that I have that length in there. So that's, you can see it's totalizing on my fence length. Because I didn't update this part number, it didn't totalize on this one. So let's get rid of that part number, make it the same as this part number up here. And now it's totalizing on there. So I have the total length of fence, whether it's expanded metal fence. I have 189 feet of chain link. I have 3.5 cubic yards in total of foundation, fence foundation for the normal size. That's one. Oh, the corner fence is a thicker one. So I'm totalizing my cubic yards. I'm totalizing my linear length of feet of fencing. And I have my total number of posts as well as in here. So I got my corner posts, my standard posts, my standard foundation, my corner foundation, chain link, total length. And this is a great output now. So when I look at the bill of material in a drawing, let's save that. So if I come into my bill of material in the drawing, my bill is going to have the total length of feet of fence I need. My bill is going to have the total amount of concrete I need, right? So here's my bill. I have all the lengths I want. I can reformat this. It doesn't have to show yards cubic 3. This can be reformatted, normal Inventor methods, right? And I have my summary. So if you're quoting to a vendor and saying, I don't need to tell them how many widgets and everything else, I just need so many feet of fence, this is a great way of doing it. This is one way of doing it. And then what, again, I would shrink wrap it into a separate part before I brought it into an assembly. If we look at the posts, I've made the post, each post in a assembly. So let's open, oh, sorry. Let's open up a, yeah. The posts, I could make them adaptive too, but it's a complicated thing, and maybe I'd rather do it with iLogic than adaptivity. I don't know. But the posts are a little more complex because it's an assembly and not a part, right? And then here, all I've done is set it up so that I put a length in. And again, this is normal Inventor practice. There's no iLogic. There's no goofiness going on. All it is math. So here I got my overall spacing. I put in my overall spacing, and it calculates the number of posts, the spacing of my last post, right? Here's my spacing of my last post. It's going to be 8 feet because I only got 10 feet as my maximum spacing. Whatever numbers you want to put in there, you can do it. It's just math. And that's how I set up the posts. And then when I put those in, I measure my point to point from my skeleton, and I know how long, what distance it is. I can go, well, from here to here, it's 1,000 inches. But anyway, that's how you measure it out, and you can go from there. So that is a method of fencing